I guess we can start the last official session of the workshop by Professor Kyungyong-Lee at University of Alabama, who is also a KIA scholar. So he's going to talk about rank 2 cluster scattering diagrams.
Thank you very much for the invitation. Okay, I changed the title of my talk because we obtained the new result last week. So, I'll talk about rank 2 cluster scattering diagrams. Okay, so in case you don't know me, my research style or my lifestyle is that I'm trying to make everything explicit and elementary. So my talk today is a good reflection of my style. So I'll make something explicit, concrete, and elementary. So basically, I want to study something like this, these numbers, and then the problem is to find the formula for these numbers. And then, these numbers, this table, is called a scattering diagram in a certain case. So I'll talk about scattering diagram. Why is it important and what is it and how can it be computed in a very elementary way? So consider any algebra that has a canonical basis. For example, a mirror of a log-Calabi-Yau variety has a canonical basis. It's expected to have a canonical basis consisting of theta functions. In particular, this explains the duality between A cluster and X cluster. I hope Michelle says something in this direction, either before or after this talk. Also, many objects related to quantum groups have a canonical basis. This algebra, if there is a canonical basis, this algebra may be associated with a scattering diagram. Let A be such an algebra and let B be its canonical basis. Then for any basis elements, B alpha, B beta, there are structural constants like this. In nice cases, the structural constant is expected to be a positive combination, sum or product of well-known numbers, such as binomial coefficients, and not so well-known numbers coming from the scattering diagram. So the mystery is actually hidden in the scattering diagram. So the scattering diagram provides building blocks for structure constants. Another object that is related to scattering diagrams is stability scattering diagram. This realizes numbers, constants as the Euler characteristic of a certain moduli scheme of representations of the associated Jacobi algebra. So that's why it is important. And then I'm going to say what it is. I cannot explain in a few minutes, and it's not related to my talk, so can I skip it? Okay. Oh, yeah, yes. Oh, yeah. I'll use the board for the time being, and then later I will use the projector again. Thank you. Although everything is expected to be generalized to a higher dimension, today I'll just talk about rank 2 or dimension 2 scattering diagram. So roughly speaking, this is related to log-Calabi-Yau, a certain special case of log-Calabi-Yau surface. Okay, so a bunch of people contributed to this Kontsevich. So naively, each two-dimensional scattering diagram is just a collection of lines and rays in the two-dimensional plane with some functions. So functions. So in the higher dimensional case, it will be R to the N. It will be collection of codimension one things, codimension one cones. So I need to define a wall. Okay, so first of all, in Michel's talk, he talked about a lattice M and N. This plays the same role. This is a lattice. So what is a pair of line or ray and a function, wall crossing function. So A is either ray so yeah, ray either half line or a full line with some slope, rational slope. This is called the support of the wall. And the function lives in formal power series of x1 and x2. Vector is okay. So once we have a direction, then this function takes the monomial to this formal power series. And these coefficients are just integers. Okay, so a baby example is like this. So this is wall, line, and then we could give something like this. 1 plus x2, 1 plus x1. So I have two walls. And also I could insert also array. So, and the associated wall crossing function will look like this. A scattering diagram are denoted by K.Y.Lee is a collection of walls such that for each non-negative integer k, the set of walls that satisfy certain conditions. Don't worry too much about this because this condition is almost always satisfied. So scattering diagram itself is not, it's just a collection, any collection of walls, but more important object is a consistent scattering diagram. So to define a consistent diagram, I need a path ordered product. So, EV and A, which is the automorphism of the formal power series. Here. And I'm just defining the automorphism, which looks like this. This is dot product. So it will be actual an integer. So integer power of the wall crossing function multiplied to each monomial, and then this primitive vector perpendicular to the wall. Yes. And just so V doesn't play much role with this V. It is used only to determine the sign. So I want to define a path ordered product. So I will define a path first. It's just really a curve. This curve does not pass through the origin. So it's just a certain generic curve whose endpoints are not in the support, and then it's meeting each wall transversally. Little v. That's right. Yeah, v has almost nothing to do with the wall. Yeah, v. Oh, yeah. That's right. It has to be non-zero. This dot product has to be non-zero. So it should not. The direction of v should not be the same as the slope of the wall. I will draw a picture pretty soon after I write the definition. Precisely, we have to consider this power k, but in practice, given a fixed k, everything is finite, so we don't have to too much worry about this. But just for completeness sake, I'm writing limit. So can so certain automorphism that is attached to the var, the S var, AS, and so on, and then composite of lots of automorphisms. So T1 through TS is just the time when the curve crosses the var. We take the tangent vector and then associated the automorphism. Take the composite of all of this, and it will form a product. So when you have a scattering diagram, we could just go the starting point and the ending point should not be in the wall. So we start from somewhere here or here or here, and then cross several walls, and then every time you cross the wall, you apply the automorphism. That will, at the end, the resulting automorphism will be called the product, path order of the product. Okay. So far I have written very quickly because I had a lot to write, but from now on I don't have to write quickly. Now let's define the consistent scattering diagram. This consistent so far there's not much going on. Everything is just it's like a generic curve, and then we have some automorphism. But this is a very strong condition for any closed. Back to the. So we are considering a loop, and then the corresponding automorphism becomes the identity. No matter where you start with, if you come back, usually nothing. If your loop is like this, then nothing is interesting because these two automorphisms cancel each other, so it's automatically identity. But what is interesting is when you go around the origin. So apply the automorphism, then at some point, if this exponent was always positive, and then we get some non-trivial power series. So it will not be identity. So this requires that at some point we should get some negative exponent, and then so negative of function should divide something. So eventually everything will be cancelled, divided and cancelled, and then becomes identity. Any questions? In practice, of course, I'll say later. In general, this is consistent scattering diagram is hard to compute. And even the existence of such a consistent scattering diagram is not immediately clear. So starting with two non-parallel walls, something like a coordinate axis, x-axis and y-axis, and then by adding many more rays, we can complete a consistent scattering diagram. So, for example, today I'm going to talk about special family of scattering diagrams parameterized by two positive integers. So my scattering diagrams will be parameterized by B and C. And B and C will determine the initial two walls. So initial two walls will, that's right. In this case, when B and C are equal to 1, I have a wall with 1 plus x1 and another wall has 1 plus x2 function. And then, okay, so, and then, oh yeah, that's right. By adding this one ray, another ray, with this function, we'll get a consistent scattering diagram. And it can be ray or lines, but usually a more interesting case is lines. Moreover, lines are actually coordinate axes, just x-axis and y-axis. Yeah, in 2006 and 2011, they only considered the surface, so it's two-dimensional. But later on, they considered the higher dimensional scattering diagram, still with coordinate, codimension 1 coordinate hyperplanes, and many, and yes. Okay, so that's right. Yeah, this is pretty simple because if B and C is 1, then it corresponds to the very simple, well-known Catch-Moody algebra. Oh, okay. Catch-Moody Cartan matrix. Okay, 2 plus 2. Okay, so the Cartan matrix. Sorry, the rank 2 Catch-Moody algebra associated with this Cartan matrix has only very few positive real roots. Actually, this corresponds to each direction. There are only 3 positive real roots and no imaginary roots. And then initially, that's right. We can do, we can start with 2 words with 1 plus x1 to the b and 1 plus x to the c. It's the simplest case. Of course, in general, we could give a polynomial with more than 2 terms, but today I'm just describing the simplest case, simplest interesting case. In general, I could replace this with a b plus 1 many terms or c plus 1 many terms. BC is 2. Cartan matrix looks like this. The associated Catch-Moody algebra has many real roots, but they form a family. 1, 0, 0, 1, 2, 1, 3, 2, and so on. Positive real roots. And in this is called the finite type, affine type, and in affine type, in the finite type there are no imaginary roots, but in affine type there is a finite family of imaginary roots. Oh, so yes, that's right. Yes. And for each root, there is a ray. It's still the same. I mean, not the same. It will be 1 plus x1 squared and x2 squared, and then so red, blue, yellow. I always multiply each component with B and C. That's just a technical thing. So basically, this just corresponds to 2, 1 real root, and so on. The next one corresponds to the next real root, and so on. So there are infinitely many real roots, and also from this side. And so on. It corresponds to 1, 2, I didn't write. And so on. And if you go from this way or this way, eventually you are getting close to imaginary root. So slope one line, ray, slope one ray. Then in this case, something interesting happening. So far, every wall crossing function has just two terms. So basically, if a wall corresponds to a real root, their wall crossing function has two terms. But if it corresponds to an imaginary root, it has infinitely many terms.
It means rays dense.
Ray?
Dense.
The collection of rays? Is it dense? If B times C are big enough, then it will be, some part will be dense, but in this case, it's dense.
Usually, we have the three types of things.
Yeah.
Rational, irrational.
That's right. Yeah, right. For an irrational type, we'll have dense rays.
That's right.
Yeah.
That's rational. Now the midline is there's a rational. Okay.
You mean every slope is irrational? Yeah. Okay. So, yeah. So basically, every imaginary root should contribute to some non-zero integer coefficient.
And then all trees, all rays have the same origin of the 0.
Oh, yeah. From the definition, every ray should be this form or this form. Yes. Vector times. Oh, yes. That's like this. So everything passes through the origin.
How is the slope determined?
Slope. Slope is determined by real root. Yeah. The line passing through 2, 1, and 0, 0 will have slope 1/2. Yeah. Okay. Slope 1. Actual physical slope will be 2b over c or c over 2b. But yeah. So in general, for finite type or affine type, probably not type E. People already studied, people were able to describe all the scattering diagrams, even in the higher dimensional case. So if B times C is less than or equal to 4, if it's strictly less than 4, it is finite type. If it's equal to 4, then it's affine type. Then E prime is easy to describe. Easy to compute, basically. And a higher dimensional case, Nathan Reading and Salvatore Stella computed scattering diagrams. Higher dimensional affine type. Okay, and then in this case things are very good.
If you is BC less than 4, that's the initial data.
Yes, initial data.
That's the initial theta and C is less than 4.
Right. Yeah. So for each pair of B and C, there is a duality between A cluster and X cluster. Since Michel skipped that discussion, I skip also. But anyway, B and C, each pair of B and C will determine mirror duality, mirror symmetry. And scattering diagram is somewhere in the middle between A cluster and X cluster.
That's I think that the symmetry between the between the middle line or middle arrows, and then between the symmetry one. Right, but
when you switch BNC,
symmetry one.
it is symmetry with respect to the relative slope of B over C. Yeah, sorry. Okay. Now, let's consider the wild case, that is B times C is at least 5. Then there are so many imaginary roots. They don't form a finite family of imaginary roots. Yeah, also, of course, there are real roots. And all real roots correspond to wall crossing functions with 2 terms. They are all simple. But the imaginary part, now if B times C is like 5, then already the cone of imaginary roots are very wide. I mean, yeah, the area would be wide. And it's, that's why it's very difficult to describe. And each wall should have infinitely many terms.
Rational or irrational?
Every slope is rational. Oh yeah, okay, so this is for this. And W is in the vector is in the lattice. So
the scattering angle theta is depending on either data you have AB, and then you get some kind of scattering angle. Depending on the scattering angle, also you have this kind of get the scattering angle. Sometimes the scattering angle would get the similar figure on this kind of the layers.
sorry, I don't understand what is the scattering angle.
We have the scattering between the 2 polygons, and then you have some kind of the scattering between momentum, and then you get the lot of the kind of layers. You have only taken the data of the exponent B and C about the depending on angle, scattering angle. The first, okay, I think the end of it we discussed.
Okay, yeah. So hyperbolic. Is it called hyperbolic? Is it? Yeah, maybe. Yes. Yeah. It's been a while since I thought about catching the algebras. Probably.
I'm talking about Uso and his company, and then Boris they work out these kind of things with some angle. I think that probably now I ask you about Boris and his company work out these particular things on scattering diagrams.
Are they physicists?
Yeah, Boris.
I've never heard.
Uso and that's they work out.
Okay, I don't. I'm not familiar with them. Yeah, I think that there is a similar construction, similar diagram. Yeah, coming from.
I ask you about.
Okay.
Uso and his company.
If what they are doing is equivalent to this thing, yeah, then yes, they are all each can be obtained from the other. The difference may be only they put rays here or somewhere else. Yeah, that's right. Yeah, something like that. Anyway, so this is very difficult. People thought it's difficult. I didn't think. There are partial results given by Akagi. He's a student of Nakanishi, and Erkin Reading and Stella. Very recently, they posted their preprint, they found a lot of patterns. Oh, Jae-sung, were you here at the beginning of my talk? Oh, okay, sorry. Can you recognize a pattern, some pattern? That's right, yes, right. Jae-sung is expert on Canada numbers, that's why. 1, 1, 2, 5, 14, 42. Yeah, if you read the coefficients along the line y equals x, then they are Catalan numbers. So, oh, this is case where B is 3 and C is 2. So wide, one of the simplest wide. And if you draw the cone of non-zero coefficients, cone like this. One boundary is like here, and then the other boundary is here. That would be exactly the same as the cone of real roots. Okay, and then but their partial results touched only a very narrow region. Like Akagi's result touched the numbers in the first 3 columns, or the bottom 3 columns. And reading Stella Ergin's result covered like a Catalan line and one off the diagonal. And anyway, they considered only very narrow regions. And Amanda Burcroff, she's a PhD student at Harvard University. With her, I said that this result was obtained last week, so we have to write down. But I'm pretty sure that each coefficient is given by some combinatorial object. And like I said at the beginning, I want to make, oh, it's already 50? Okay, I want to make everything very explicit, very elementary. This combinatorial object is very elementary. Even high school students could understand.
You can use more time.
Thank you. Okay. So I want to describe comparable pairs. I think God gave these combinatorial models, but I discovered around 10 years ago. Schiffer and I kind of discovered prototype of comparable pairs, and then Lee made the current version of comparable pairs, and then Zelewski wrote concise mathematical definition for comparable pairs. So I think this is this should be a fundamental object, although I didn't know before. Okay, anyways, the object is dyke path. So a maximal dyke path is something like consider any grid, like any number of horizontal edges. So anyway, it's just an m by n rectangle. Both are integers, and then draw a diagonal. It is a lattice path, but we have to. Okay, let me use a wiggly line. The maximal dyke path consists of east steps and north steps. But it should, and then it does not go above the diagonal, but it has to be closest possible to the diagonal. It's just labeling of horizontal edges and vertical edges. So I have this many horizontal edges and vertical edges. Everything, so to describe a comparable pair, everything will be just a horizontal edge and vertical edge. So it's very easy to describe. Oh, I already draw a picture here. Yeah, this after refining all the definitions of comparable pairs that Schiffler and Lee and I discovered. Zelewski streamlined and then made it concise like this. But maybe if this is the first time for you to see this kind of a thing, then it may be hard to understand. So I will just I will try to describe. Can I turn on the light? Oh, thank you. So comparable pair is just a pair of chosen horizontal edges and vertical edges. If I, okay, let's say, so always B and C are fixed. Let's say I choose these two horizontal edges. And then, okay, let's do some sort of feng shui. There is a city, and it's facing the ocean this side, and then there is a mountain. I'm going to build an apartment complex. Every apartment is just flat, one floor, but it has B many rooms or C many rooms. For a horizontal edge, for each horizontal edge, we build an apartment that has C many rooms first, attach it to this thing. So I'm drawing 1 by 2 rectangle here, and then also 1 by 2 rectangle here. And then each apartment, each room has a window facing to the ocean. So there's a window, window. And in each building, in each apart, there is a family, and each family member, there are C many family members here. But the person who is living in this room cannot see the ocean because this building is blocking the view. So he is disappointed. So the family all together decided to move. So they built a new building, attached it to the one before, and then so build another apartment, and then move. Since they are family, they move all together. And then once, but after they moved, you don't destroy all the apartment. It's still there, although it's empty. So now I have 3 1 by 2 rectangles. Now everyone is able to look at the ocean, so everyone is happy. And then for a vertical direction, if I choose these two, even if I have many horizontal edges, I do the same game. For vertical direction, do the similar thing. Now I have each apartment has 3 B many rooms. Draw 3 by 1 rectangle, 3 by 1 rectangle. These two people are not happy, so they move, build a new apartment, and then moved all together. So we built such an apartment complex. Any question? Probably I'm too quick, but okay. And 0. This is good. Yeah, the cluster algebra, rank 2 cluster algebra corresponds to rank 2 Kac-Moody algebra. And yeah, if we switch from Kac-Moody to cluster algebra, we consider a skew symmetrizable matrix. So diagonal becomes 0. But there is not much difference. It's just the notation. Anyway, the mathematical definition is trying to capture this thing. So, okay, let's do it quickly. So to recap, I have a 6x4 maximum dive path. Choose the first 2 horizontal edges and build the apartment complex. Then I get blue buildings. Choose the last 2 vertical edges, then I get red buildings. But the problem is that blue and red overlap here. So in this case, we say that these pair of horizontal edges and vertical edges is not compatible. In this case, it's good. There's no overlap between vertical pieces and horizontal pieces. So this is it's called a compatible pair of horizontal edges and vertical edges. And the coefficient in the scattering diagram is the number of compatible pairs okay. It's hard. I don't need it anymore. Okay. It has a rational slope, array with a rational slope. And then this is like blah, 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 C1, X1, and 1. This number, to get this number, we need to consider consider this as a vector. So take a dot product, and then we want this to be positive and minimum possible. So if M1 and M2 are co-prime, relatively prime, then we want the dot product to be equal to K. Choose such a pair of positive integers. It will determine the size of rectangle, size of maximal dive path. And then count certain special compatible pairs. Subset of horizontal edges, subset of vertical edges. And the cardinality of each subset matters. It has to be like this. And special means okay. Right. It's quicker to, I'm already spending too much time. So just the last sentence. Special means either blue complex shadows red or red complex shadows blue. In this case, it's not comparable, so we don't have to consider. This is comparable and special. And shadow means for the shadow of the blue buildings is the shadow or the actual physical shadow when the sun is here. It's shadowing everything. So the shadow of this building, blue complexes, shadows all vertical edges. So in this case, it's called special. But blue buildings do not shadow these horizontal edge. But that's okay. Either way, it's fine. So if we just count those special comparable pairs, then we get the actual coefficient. And it's the end of my talk. Thank you.